today is to talk about galaxy clustering. And to finish talking about galaxy clustering. And hopefully towards the end also to discuss some of the main systematic or sources of systematic uncertainty that affect large-scale structure observables from galaxies, so cosmic shear and galaxy clustering, all right? Let's see how far we can get. All right. Say that again? Yes, this is how delayed I am with my lectures. I thought I was going to be able to talk about this yesterday. So yeah. Anyway. All right. So galaxy clustering. The idea in galaxy clustering is as a proxy for the thing that we want to measure, which is the matter over density. Instead, we're going to look at the galaxy over density. All right, so the number of galaxies or the number density of galaxies in a given position minus the mean divided by the mean. All right, you've already seen with Roman last week that the relationship between the overdensity of galaxies and the overdensity of matter is in principle quite complicated, right? So this relationship is, in general, nonlinear, non-local, and stochastic. But we have good reasons to expect on sufficiently large scales there should be a linear relationship between the two of them with a free parameter that we call the galaxy bias, right? We saw, for example, an argument for that coming from the peak background split in the halo model when we talked about that. All right, anyway, we know that this is a okay model, but not a really good model, right? So with Raman, for example, you saw perturbative expansions of galaxy bias that allow you to drill a bit deeper into the nonlinear regime, but we always have this problem with galaxy clustering, right? We don't know exactly what the relationship is. On large scales, it should be linear. But what does that mean in terms of the power spectrum? So if we're measuring the power spectrum of galaxies, what this tells us is that on the scales where this holds, then the power spectrum of the galaxies is going to trace the power spectrum of matter with an unknown amplitude, right? So it will kind of look like the power spectrum of the matter fluctuations, but with an unknown amplitude. So we don't know exactly actually what the amplitude is. And that prevents us from, for example, directly constraining sigma 8 from galaxies, right? Because we don't know what the actual amplitude is of this power spectrum. And then moreover, on small scales, we actually don't know very well what's going on, right? So that's where nonlinear bias will start kicking in, and we don't know exactly how to. Well, we know of several approaches that can solve this problem, but they all involve free parameters that we need to measure with our own data, right? We don't know this relationship from first principles. And just to give you an idea, what scales are we talking about? The equality scale that defines this peak in the matter power spectrum is about 0.01 inverse megaparsecs. The BAO typical scales is about 0.1 inverse megaparsecs, right? And so you're talking about scales beyond about 0.1, right? And we saw in one of the first lectures that the matter power spectrum, the nonlinearities in the matter power spectrum at low redshifts, they start kicking in around here, right? Around 0.1, 0.2. And that's also, so the case for bias is going to be even worse than that, right? So that's the kinds of scales where you need to start worrying about nonlinear bias. So the perturbative expansions that you've seen with Roman, they'll allow you to push maybe a little bit into the 0.2 kind of regime for galaxies. There's fancier models that have come up recently. There's something called HEFT that I'm kind of excited about. This is a biasing scheme called hybrid effective field theory. So it uses perturbative expansion at some level in the kind of initial conditions of the universe, but then it uses a simulation to simulate the gravitational evolution of galaxies. And that can actually allow you to push into scales of the order of 0.4 maybe inverse megaparsecs, right? So that means you go beyond the BAO scales and start probing into the nonlinear regime. But overall, it involves a lot of new free bias parameters that we need to constrain with the real data. And you saw some of these with Roman. Yes. Ask me in the Q&A, because otherwise I will not have time to finish talking about this. But it's something I'm excited about. Yeah, I can tell you more later if you want. Yes. Yeah. So I'm not going to talk about galaxy bias, because otherwise we'll not finish. I'll try to basically be complementary and talk about things that Roman didn't talk about. Okay? So I'm going to skip. You can see skipping my notes for a while, because I was going to talk about bias. Right. So let's talk about what are the main observables that we can get from galaxy clustering, right? So there's two ways of trying to extract cosmology from galaxy clustering, and it depends on what kind of data you have, right? If you have spectroscopic data, meaning that you know the redshift of each galaxy, then you can do a 3D analysis of these galaxies. And what does that mean exactly? So if you have a redshift for each galaxy and you know that this redshift is correct, then you can infer, if you assume some cosmological parameters, what the distance to that galaxy will be, right? And that means that you can put them in 3 dimensions. You know the angles, you know the distance, you can put them in 3 dimensions, and you can construct a 3-dimensional map of the galaxy over density in 3D, right? So this is now a 3D vector. So that's great. Okay, then we measure the power spectrum. We compare it with some kind of bias model and then infer cosmological parameters. But there's actually a caveat here, which turns out to be a very nice caveat. And it's the fact that in order to do this, we need to assume some cosmology, right? When we transform redshifts into distances. So this is actually not a universal function, right? This depends on whatever cosmological parameters we have assumed. So what happens if we assume the wrong cosmological parameters, right? I'm going to assume that we have used a fiducial cosmology, maybe something close to the best fit from Planck or something like that. I'm going to call that the fiducial cosmological parameters. What would be the true 3-dimensional position of a galaxy? Well, it would be psi of the z for that galaxy given the true cosmological model times the unit vector in the direction of the galaxy, right? And this would be the chi for the true cosmology divided by the chi for the fiducial cosmology times n. Sorry, times x for the fiducial cosmology, right? The one that we would assign this galaxy in our analysis. All right? Okay. So we have these relationships between the true coordinates and the 3-dimensional coordinates and the inferred 3-dimensional coordinates. And then what we're going to do is we're going to take these galaxies and maybe look at the power spectrum or the correlation function, right? So let's think in correlation function space. Correlation function basically means we're going to compare the density of galaxies that we find in this point and in this other point, right? And as a function of the separation between these 2 points. So let's say that we have 2 points separated. So we're looking from here. And we have 2 points that are separated along the line of sight by some separation in the parallel direction, right? Or equivalently, 2 points that are separated by a given redshift separation, small increment in redshift. Okay. Well, then we know that the 2 would be related by delta z divided by the expansion rate for the true cosmology, which then is the expansion rate for the fiducial cosmology divided by the expansion rate for the true cosmology times the separation in the fiducial cosmology, the one that we would infer. Okay. And so that means that radial distances are perturbed by a factor, which is given by the ratio between the expansion rates in the fiducial and the true cosmology. This is what we usually call alpha parallel. And the same thing, we have now 2 galaxies roughly at the same redshift, but separated by some angular separation, delta theta. What would be the separation in the transverse direction? The separation in the transverse direction would be the radial coordinate times delta theta. And this would be the radial coordinate in the true cosmology divided by the radial coordinate in the fiducial cosmology times the separation, the transverse separation in the fiducial cosmology, so the one that we would infer. Yes, so this is what, this effect is what we call the Alcock-Paczynski effect, right? The fact that once we put things in 3 dimensions, the fact that we've assumed a cosmology and that cosmology is probably wrong, that will perturb, that basically will stretch or compress distances in the transverse and longitudinal directions by different factors, okay? This is the Alcock-Paczynski effect. I'm going to try to spell this. Alcock, and Paczynski is the difficult name. And I've probably misspelled it, so maybe don't put this on YouTube. All right, so what does this mean then for our measurements, right? How can we incorporate this into our measurements? All right, let's imagine we have a measurement of the power spectrum. We know what the power spectrum looks like. It's easier for the Alcock-Paczynski effect to understand it, to think of this in terms of the correlation function. The correlation function will look something like this. And any sinusoidal contribution, like the baryon-acoustic oscillations in Fourier space, if you do a Fourier transform of a sinusoid, you get a delta function, right? So instead of a delta function, you'll get a kind of a bump here, right? So this is psi of r as a function of r. And this bump here is is just the BAO bump, okay? And it's a separation given by the sound horizon at the drag epoch close to recombination. All right. So let's imagine that instead of measuring this, what we're going to measure is the 2D correlation function. So that means correlation function as a function of both the separation along the line of sight and the transverse direction. So I'm going to call that R perpendicular and R parallel. Okay? All right, so what is the observed correlation function? The observed correlation function would be the same as the true correlation function, except in the shifted separations, right? So it would be the true correlation function at alpha perpendicular times R perpendicular and alpha parallel times R parallel. Okay? So let's say that we make a 3D plot of the correlation function as a function of both of these coordinates, R parallel and R perpendicular. And so in the Z direction here, we have the amplitude of the correlation function, and I'm going to draw some contour plots of that correlation function. If we had exactly the right cosmology, what should those contour plots look like in a statistically isotropic universe? Sorry? No, so what I mean is we have this, right? And I'm plotting this as a function of the transverse and perpendicular separations, right? So this would be if transverse and perpendicular separations are equivalent in a isotropic universe, then you would just get basically the kind of rotation of this curve along this axis, right? So those contour plots would just be circles, right? Like that at different. Does that make sense? Yes? Okay. And moreover, one of those circles will be the circle that passes through the BAO, right? So the one at RS. Let's say that this is the one at RS. This is RS. All right, but if we have the wrong coordinates, the wrong cosmology, then we will be stretching the parallel and perpendicular directions by different amounts. So what you'll get is that, for example, the BAO feature will be a bit larger, or it will appear at a slightly larger coordinate, but also that slightly larger coordinate will be different in the perpendicular and the transverse direction. So it will no longer look like a circle. It will look like some kind of squashed things in one direction or another, depending on the cosmology that you have, right? And we're interested in the BAO in particular because this correlation function is kind of boring. But if you're shifting this correlation function, the easiest feature to pick out is this bump here, right? So what we can do, right, is we can vary cosmological parameters, the ones that we, away from the fiducial ones, and then see at which point we get the BAO feature, for example, at exactly the place it should be, because we know what the sun horizon ad recombination is from the CMB very well, right? So we can do that, and not only that, but the fact that we can do that in the two different directions allows us to both measure the distance redshift relationship directly, so chi, but also the expansion rate directly as well, right? So this is kind of the rough idea of how we do, how we extract information from the baryon acoustic oscillations peak, the BAO, which I assume you've heard about, right? This is a bit easier to understand in terms of the correlation function, but you can do the same analysis in terms of the power spectrum. The only thing that you need to remember, right, is this is the relationship in the correlation function. The power spectrum is the Fourier transform of this. A Fourier transform involves an integral over distances, but those distances now have been stretched, so you need to account for that stretching in the Jacobian of that integral, right? So this relationship for the power spectrum is the same, except it picks up an extra normalizing prefactor from that Jacobian, right? So this, the P of K perpendicular K parallel, the observed one, will be the real one at the stretched values of K, because these are Fourier modes. The alphas now will go in the denominator. And you have an extra factor here, a normalization in the form of alpha perpendicular squared, because you have two transverse coordinates, and alpha parallel to the minus first. And this comes from again from the Jacobian that translates from the true coordinates to the inferred coordinates. Okay. So if you do the analysis in Fourier space, you need to account for this effect as well. And just to give you an idea of how much the field has progressed, this is the first measurement of the BAO back in 2005. I think this is the first detection of it. So it's very useful to have those lines there because they allow you to see the BAO feature very well. But if you imagine that you don't have those lines and you just look at these points, to me these points could be very well fit by a single power law, right? So it's this bump here is barely visible, really. So it was 2005, and then in 2025. So the latest measurements from the DESI experiment, right? Is I'm zooming into this bump, and you can clearly see that there's a very well resolved and very clear bump. And this is now done for 6 different samples of galaxies at different redshifts, right? So you can definitely see a bump in the correlation function at really high signal to noise, right? And so you can imagine if you use the wrong cosmology, right, you will be shifting this significantly away from this point. And the fact that you've been able to resolve this BAO so well means that by resolving it so well, that means that you can actually constrain these distance ratios really, really well. So usually the constraining power, or the precision with which we can infer alpha parallel, alpha perpendicular, for example, is at the level of 1% with current data, right? So then BAO is one of the most precise, I guess, probes of cosmology that we have. These ones, I think I'm gonna guess that they're post reconstruction, but I'm not completely sure. Yeah. So and then you can ask me about reconstruction later, for those who don't know what that is. Yeah. Questions? No? Oh, sorry. They depend on 2 cosmologies, your fiducial cosmology, which you know, and so you can always, this part of alpha parallel, right? Then you measure alpha, and if you have a measurement of alpha, then that allows you to then infer what H true is, right? basically. Yeah. That's the idea. Yeah. Yes, that's a good point as well. So I said that we know exactly what the sound horizon is, but it's not true, right? The sound horizon depends on cosmological parameters as well. It depends on omega m, it depends on omega b, right? So strictly speaking, the parameter that you can constrain very well is this ratio, right? It's h fiducial divided by h true, multiplied by the ratio of the RS in the, I think it's the true cosmology here and the fiducial cosmology here. Don't quote me on that, but yeah. So it's usually that ratio that you're the most actually sensitive to. Yeah. So the idea in a BAO analysis is that you would play this game, but you wouldn't play this game with the full correlation function. You would play this game with the BAO part of the correlation function, right? And if you do that, then you can see that naturally you also pick up a factor of RS in doing that, basically. Yeah. Yeah. And that's because the BAO feature is the most sensitive part of the correlation function to cosmology, basically. Yeah. Or to the Alcock-Paczynski effect, rather. Yeah. Okay. All right. The other main observable that we have, if we look at the 3D clustering of galaxies, is redshift space distortions. And again, this is something that to some extent you've seen with Roman. So I'm not going to derive the redshift space distortion effect, but mostly just discuss very briefly the kinds of things we need to worry about when we look at redshift space distortions. So I'm guessing that with Roman, you already saw that the power spectrum for galaxies, after accounting for redshift space distortions, so redshift space distortions is the fact that this redshift that you measure for each galaxy is actually not its cosmological redshift. It's cosmological redshift plus the Doppler redshift coming from its radial velocity, right? And remember that I'm using natural units. All right, and that essentially causes an extra distortion in the power spectrum that makes it anisotropic. So the power spectrum, if we write it in terms of the modulus of k and mu, so mu is basically the angle with respect to the line of sight, so k parallel is k times mu. That's the definition of mu. You saw that this takes a kind of nice form where you have the, assuming linear galaxy bias, Bg plus f times mu squared, all of it squared times the power spectrum of k, right? The one without redshift space distortions. Right. Okay. So and this is very nice because that means that by looking at the anisotropy in the power spectrum induced by this term here, we can pick up, we can break the degeneracy between the linear galaxy bias and f, where f was the growth rate, right? So that allows us to measure these two quantities. So it allows us to measure Bg times sigma 8. Remember that we have the amplitude of the P of k depends on sigma 8 squared. So we can measure that, and separately from that, we can also measure f times sigma 8 from redshift space distortions. Okay, you know, this is not very useful because we don't know what the galaxy bias is, so it doesn't really tell us much. But this is purely cosmological, right? It doesn't depend on galaxy bias. So it allows us to say something about the growth of structure at late times, which will be affected by dark energy. Yep. Oh, okay. You know what sigma 8 is? Right. So, okay. So in Manu's lectures, you've seen AS, I guess, as a cosmological parameter, right? The amplitude of linear fluctuations. And so the amplitude of the matter power spectrum later on, right, will also depend on AS, right? For large-scale structure, we usually don't think in terms of AS. We think in terms of sigma 8 as a parameter that parameterizes the amplitude of the power spectrum. Sigma 8 is defined as, so sigma 8 squared is 1 over 2 pi. So it's basically the variance of the power spectrum on spheres of 8 h inverse megaparsecs, right? I'm not sure if it's worth me writing the equation for this. I'm not going to write it, and then you can ask me about it. But it's basically proportional. It's some integral, right, that involves the power spectrum, right? So it's a way for us to parameterize the overall amplitude of the power spectrum, basically, right? So the same way that we don't know AS unless we measure it in real data, we don't know sigma 8 unless we measure it. So that's one of the cosmological parameters that we would like to measure in principle from galaxy. Yeah. Usually you would use one or the other to do cosmological constraints. You can't, one is a derived parameter of the other, basically, yeah. Yes? They do, because sigma 8 doesn't just depend on AS, right? It depends also on all the other cosmological parameters that affect P of K. So there isn't like a one-to-one relation between the two of them, unless you also know all the other cosmological parameters. The reason why we use sigma 8 in cosmology for large-scale structure is, in my opinion, purely cultural. People started using that when they started doing large-scale structure, but yeah. Great. All right. So I'll just maybe remind you of a couple of things. So you know that this effect is only, so this description of redshift space distortions is only valid on large scales, right? This is called the Kaiser effect. And the Kaiser effect is only valid on relatively large scales where you have linear bias, where the relationship between velocities and densities is linear, so you can use the continuity equation to write this in terms of f, etc. But in non-linear scales, that's not true anymore. And I think Roman already told you about this fingers of God effect. Does that ring a bell? Yes? Okay. You can see those in action here, right? So this is an image from, I think this is from a simulation or from a real catalog where the fingers of God are subtracted afterwards or something like that. This is essentially the same galaxies, except one of them don't have redshift space distortions, and the other ones do have redshift space distortions. And you can see on small scales, you get these lines of galaxies that align with the largest overdensities in the sample, right? So this is, in the nonlinear regime, you have this kind of flipping of galaxies, flipping of the observed positions of galaxies due to fingers of God, and it seems like all those fingers, all those lines are pointing at you, at the observer, right? So that's why they're called the fingers of God. What that means in terms of the correlation function, so this is the same plot that I was trying to draw very poorly here, but now in a proper plot, right? So these are contour plots of the correlation function as a function of pi, which confusingly is what we use for R parallel. So this is the distances along the line of sight, and RP, this is R perpendicular, okay? Right, so on large scales, you see this squashing, which is not due to the Alcock-Paczynski effect. So in this case, you have the right cosmology. This is actually the squashing due to the mu squared term that you have over there. So this is the Kaiser effect. But on very small scales, you start seeing the opposite, right? You have this elongation of the contours, and this is the fingers of God effect. So you can already see that even on large scales, right, 20, 30 megaparsecs, the fingers of God effect is still there, right? So redshift space distortions is actually a nuisance. Well, it's a good thing because we can measure f sigma 8, but also we need to be very careful because the effects of nonlinearities due to these velocities can extend out to relatively large scales. So that means that in a real galaxy clustering analysis, you need to worry about nonlinear bias, you need to worry about the nonlinear power spectrum, you need to worry about nonlinear redshift space distortion, and including the fingers of God in your modeling. So this kind of simplified picture here gives you the right idea of what's going on, but in a real analysis, you need to account for all of these effects. Questions? Yes? Yeah. Are what? Yes, yeah, you measure that from the measure, yes. That's right. Yes, yes. Yep. Yeah. So in fact, there's kind of two philosophies in analyzing 3D clustering. One of them is we should just take the power spectra or the correlation functions and just do a forward model that directly connects them with cosmological parameters, including the Alcock-Paczynski effect implicitly and all that. But that should all be part of the forward model. And we get all the information at once, and we're done. The other kind of way of thinking about it is, instead of that, what we should do is we should measure pure observables, meaning quantities that we just extract from the data that can then be used to infer any constraints about any cosmological model, right? So the alphas, for example, they do not depend on cosmology. They just depend on your data and the fiducial cosmology that you choose, but not on the... So you could just measure them directly from the data and then just use those to then constrain cosmology afterwards. And the same thing with F sigma 8. This is something that you can extract directly from the data. The question is whether all of the information that we can get from galaxy clustering can be compressed into those three numbers, alpha perpendicular, alpha parallel, and F sigma 8. And the answer is no. So if you actually want to extract all the information, maybe you want to do this forward modeling thing, which is more costly. So this is called the full shape analysis of the power spectrum. But I think it's still quite valuable to extract these numbers, right? Because these numbers do contain a lot of the information. So by looking at these numbers, you can learn a lot, not just about the cosmology, but potentially about systematic effects in your data and things like that. Yeah. Yep. Yeah, that's a very good question. And the answer is yes. So the question was whether by looking at that we can tell whether that squashing is Alcock-Paczynski or redshift space distortions. And the key to all this is the BAO. The BAO is not really moved by redshift space distortions that much, right? So any squashing of the BAO is pretty much just Alcock-Paczynski qualitatively. Yeah. Yeah. And you can see that the BAO is not here, right? The redshift space distortion. Sorry, the sound horizon is at 100 megaparsecs, so that's here, much farther away, right? Great. Okay, so that's it for the 3D clustering of galaxies. That means when we have spectra, and therefore redshifts. But very often, we don't have spectra. What we have is photometry for each galaxy. What that means is that what you've done is you've taken your telescope, you've pointed it throughout the sky, and just taken pictures of the sky through different filters, right? So instead of measuring the spectrum of any of these objects at narrow bands of frequency or wavelength, you've only taken an image that basically integrates the whole spectrum over a given range of frequencies, a broad range of frequencies, right? So in the end, you end up with a very poor measurement of the spectrum at, let's say, 1, 2, 3, 4, 5 points, right? So this will be a really crappy measurement of a spectrum, which means that you will only be able to extract a very crappy measurement of the redshift of that galaxy. And that crappy redshift is what we call a photometric redshift, okay? What that means in practice is that we don't really know in a photometric redshift survey exactly where our galaxies are in the radial direction. And the redshifts that we infer are usually quite dangerous to use as a real redshift, right? Because we don't. It's hard to understand at the galaxy by galaxy level how uncertain the redshift that we have measured actually is. Okay. So in practice, what we do is we use the photometric redshifts to get a rough idea of where our galaxies are in redshift, and then we bunch them up into groups that we call photometric bins or redshift bins. So groups of galaxies that we think are roughly at the same redshift. Okay. And then we just look at the angular statistics of these galaxies instead of looking at the 3D statistics of the galaxies. Okay. So what does that mean exactly? So instead of counting the number of galaxies that we observe in a given 3D volume and use that to construct the 3D delta G of X, we will just get all our galaxies in a given redshift bin and then look at how many of them we have in a given solid angle and then look at what we call the angular overdensity, right? So the angular overdensity of galaxies as a function of position on the sphere will be the angular number density of galaxies in that position minus the mean angular density of galaxies divided by the mean angular density of galaxies These little omegas are here just to remind you that these are angular densities. All right. Well, you can show that this is, you can relate it to the three-dimensional overdensity of galaxies as through another of these line-of-sight integrals. So it would be an integral over all redshifts of the redshift distribution of your galaxies times the three-dimensional galaxy overdensity. All right? And remember that when we were looking at weak lensing, we like to write these integrals in terms of comoving distance rather than redshift, so I'm going to rewrite it that way. So integral over comoving distance. Comoving distances and redshifts are related by a factor of h. And this is the final observable quantity that we have, right? What we measure is a map, a 2D map of our galaxy overdensity. And if we want to relate it to the three-dimensional one, we need to account for the projection over the redshift distribution of our galaxies. All right, so this then is what I would have called in my previous notation QG, right? The radial kernel associated with galaxies. And we already, and this is something that is proportional to the redshift distribution directly, right? So we saw that for weak lensing, if you had galaxies with a given redshift distribution, the lensing kernel was this broad thing. For galaxy clustering, the redshift the radial kernel is just the redshift distribution itself. So galaxies, what that tells us is that galaxies are local tracers of the large-scale structure. If we measure the overdensity of galaxies at this redshift, we're directly probing the matter overdensities at that redshift, okay? This is the key to understand how we can extract information from the projected clustering of galaxies, okay? So it's basically using the properties of locality. So the first thing is, remember, if I go back to my very old slides, if we look at the clustering, the angular clustering of these galaxies, we need to go back to the Limper equation that we had here. And remember that a given angular scale is related to a physical scale by simply dividing by the comoving distance. If our kernels now are narrow kernels, then we actually know to some extent what the distance to these galaxies is, right? So that means that we will be able to relate a given angular scale to a given physical scale. So in other words, we can still, hopefully, if this P of Z is not too broad, we can still relate the shape of the angular power spectrum for these galaxies with the shape of the matter power spectrum, which is useful, right? And so let me give you an example of that. So this is, I'm not going to show you what the redshift distribution is for these galaxies, but it's actually pretty broad. And what I've shown here is a prediction for several things, right? So we have, in red, we have the angular power spectrum for galaxies in a given redshift bin. So it's a fairly broad, you don't need to know what it is. And then in blue, I'm showing the P of K evaluated at L plus 1/2 divided by the mean redshift of all of these galaxies. And then I've scaled it by a random factor. Not a random factor, but something that matches this amplitude here. And the main point that I'm trying to make here is that this is a simplification, right? I've effectively, in the Limper equation, I've just pulled the power spectrum outside and just evaluated it at the mean redshift of the galaxies. And that's actually a fairly good approximation, right? We're clearly recovering the actual shape of the matter power spectrum by looking at galaxies. So the locality of galaxies allows us to measure the scale dependence, okay? So scale dependence, it will also allow us to do tomography. What do we mean by tomography? Tomography means let's take galaxies that we know are roughly at a narrow range of redshifts and cross-correlate them with other quantities that are integrated in redshift, right? Meaning quantities like this, let's say some quantity x, sorry, Rogerio, which is a projected tracer of some 3D quantity physical object, okay? Remember, this could be the semi-lensing convergence, for example, which is a tracer of the matter fluctuations along the line of sight. And if we take this, which has a broad kernel, and cross-correlate it with galaxies at a narrow range of redshifts, then that cross-correlation will be sensitive to this quantity, but only at the redshifts of the galaxies that we're cross-correlating with, right? So that will allow us, to some extent, and we'll see how later, to reconstruct the cosmic history of this quantity by slicing it up through cross-correlations with different galaxies, okay? Yeah. The red, right, yes. So what I'm showing here is, imagine that you have some projected quantity that has a very broad kernel, and then you cross-correlate this with galaxies at different redshifts, and what this is supposed to represent is the redshift distribution of those galaxies at different redshifts. And my point is that the amplitude of that cross-correlation, we will see, is going to be proportional to the amplitude of x at different redshifts. So you can reconstruct the cosmic history of that quantity by looking at these cross-correlations, and I'll show you a few examples later of that. Yeah.
So then you're implying that you can only do cross-correlations in 2D?
You can do it in 3D as well. No, you can do it in 3D. It's just that in 2D you can still do this. For 3D, you can also do that for. If you have spectra, it's great. But if you don't, you can still do this. Yeah, yeah. Right. So about the scale dependence, what do we care about the scale dependence of the matter power spectrum? There's two things we care about. One of them is this broad peak. Unfortunately, this broad peak, the one due to the equality epoch between matter and radiation, is unfortunately it happens at very low, very large scales, right? So reconstructing it sometimes it's tricky, but we can actually do this, and there's been a few papers actually reconstructing that from photometric surveys. The other one that is quite prominent in the power spectrum is the BAOs. But you can see what happens if we have a broad kernel of galaxies, right? So if we have, let's say, as a function of position, we have chi of r. If we had galaxies at a precise redshift, and we were looking actually not at chi of r, but chi of theta, right? So the angular correlation function. What we should see is just the 3D correlation function, but with a bump at the scale theta s, which is just rs divided by the distance to these galaxies, right? But now if we have galaxies over a broad range of redshifts, let's imagine that we have the contribution from galaxies at lower redshifts, for example. At lower redshifts, this peak will appear at higher angles, right? So you will get a contribution from galaxies at lower redshifts that will look like this, basically. And then if you have galaxies at higher redshifts, the correlation function will shift in the opposite direction. So if you have a broad distribution of redshifts, that's going to do two things. First of all, it's going to shift the BAO peak around, so it might bias your inference of the BAO. But more than that, it's going to broaden it, right? So it's going to look less like a peak and more like a crappy hump that you can't really do much with. And you can see that in this figure here. It's a bit subtle, but the power spectrum, the broad shape is very nice, right? But if you look at the BAOs, in the true power spectrum, you can definitely see those oscillations a bit better, right? Whereas the one that accounts for the width of the redshift distribution, those BAOs are kind of smoothed out, right? The amplitude of those oscillations is much lower. So you can, in principle, do 2D BAO. But you need to worry about these projection effects, and also the usual precision with which you can do BAO in 2D is usually a lot worse than the spectroscopic BAO, right? Yeah. All right. So let's talk, instead of talking about the BAO, let's talk about the tomography aspect. What did I do? Here, all right. So let's consider the cross-correlation. Where's the, here. Let's consider the cross-correlation between galaxies at a given range of redshifts and some projected quantity. I was calling it x before, but I'm going to call it u now. All right, so we saw that using the Limber equation, what that is d chi squared qg of chi, and then the radial kernel for this quantity that we're correlating with, and then the power spectrum between galaxies and that quantity that we care about. Okay. And let's say that we're doing this on large scales. Okay, so on large scales, we can use linear bias for the galaxies. And also, remember in the halo model, for any quantity, we always had this two-halo regime on large scales, right? So what would this be according to the halo model? On large scales, this would be the bias of our galaxies times, remember there were these quantities I called BU for any other quantity. I'll tell you what this is in a second, times the matter power spectrum or the linear matter power spectrum. And BU, remember, was the mean value of this quantity integrated over halos of all masses, right? So it was something like this. Times the halo bias times the quantity that we care about, U of M. Okay, so now, in most cases, we know what the radial kernel is for our quantities. So in the case of CMB lensing, we have an idea what that radial kernel is. For Sunyaev-Zeldovich, as you will see with Manu, you also know what the radial kernel is. But very often, what you don't know is actually what the value of this quantity is as a function of redshift. Okay. However, if this redshift distribution of our galaxies is narrow enough, you can expect then that the evolution of this quantity as a function of redshift, that will change much more slowly than this, right? Than a sharp redshift distribution. So we can approximate this integral by just pulling out both the galaxy bias and BU evaluated at the mean redshift of these galaxies, right? So BG and then BU at the mean redshift of the galaxies times d chi divided by chi squared, QG, QU, and then the matter power spectrum. Okay. Right, so now let's look at the ingredients here. So we have the galaxy bias. We have the bias-weighted mean of some physical quantity at the redshift of the same galaxies. And now we have here a power spectrum, an angular power spectrum that only depends on cosmological parameters, right? Depends on the kernel of our galaxies, and that's just the P of Z. And then the kernel of this thing, which we said we know, and then the linear power spectrum, which will depend on cosmological parameters. So this is a pure cosmological quantity. And this is something we don't know about the physical object that we've cross-correlated with. And we also have an uncertainty on BG, but we can use CL, the autocorrelation of our galaxies, which will be proportional to BG squared times a similar integral like this. That only depends on cosmology. We can use this autocorrelation to figure out what the bias is. And then if we combine that with the cross-correlation, then that allows us to measure BU as a function of redshift. You need to worry about the remainder, right? We said this depends on cosmological parameters. So there's two attitudes here. First attitude is to say, maybe let's say we know cosmology. We just fix those cosmological parameters to Planck, because Planck is pretty precise anyway. And what we care about is using these cross-correlations to learn about some other physical quantities. And I'll give you two examples later. Fine. The other option is to try to incorporate any uncertainties in the cosmology in here. So what's the main thing that will affect this power spectra? It will be, first of all, sigma 8, which controls the overall amplitude of this thing, right? So what you will measure actually is not really BU, but BU times sigma 8, if you don't want to know what sigma 8 is. And the other thing that mostly affects the shape of the power spectrum on large scales is omega m. So omega m kind of defines the omega m and h, I guess, define this tilt here, the slope of the power spectrum in this direction. So if you want to account for the cosmology effect, then you need to incorporate it here. But otherwise, if you just say, let's assume that Planck is the truth, then you can use these cross correlations to reconstruct BU. So let me give you two examples of these. So the first one, actually, let me show this one first. The first one is cross correlations between galaxies and the Sunyaev-Zeldovich effect, which I think you haven't seen yet with Manu. But the Sunyaev-Zeldovich effect is something you can extract from the CMB that is directly probing the pressure of the intergalactic medium, of all the gas in the universe, basically. So this is an analysis that a student of mine did, Nick, where he took maps of the Sunyaev-Zeldovich effect and cross-correlated that with galaxies. And what that allowed him to do is to measure the pressure, the mean pressure of the universe as a function of redshift over a bunch of redshifts, basically. And you would say, okay, well, that's cute. And if you're an astrophysicist, that's maybe interesting to you. But I'm a cosmologist, so this is maybe not so interesting to me. But if we think about it, what is this? This is the pressure of all the gas in the universe. What did we say about gas the other day? That the distribution of gas actually affects weak lensing through baryonic effects, right? So this is a way to extract information on a quantity that directly probes that gas, right? So you can potentially constrain baryonic effects by comparing these measurements with predictions from different hydrodynamical simulations, for example. So this is something that is useful to do. But then the other way to think about it is you can do cross correlations with CMB lensing, for example, right? And in that case, BU is just 1, right? Because the matter fluctuations have unit bias. And you can then use the cosmology dependence of the rest to constrain something, right? And the main thing that you can constrain is sigma 8 by playing the same game. And this is what Julia did, who I think is working with you a couple of years ago. And the nice thing about doing this with CMB lensing is that CMB lensing, as we said, covers all redshifts, right? So if you get galaxies at sufficiently high redshifts, you will always be able to cross-correlate them with CMB lensing. And this was a paper where she made measurements of sigma 8 at very, very high redshifts. So some of the highest redshifts, I think, where this has been done. So this is kind of a nice thing to, a nice way for us to use photometric clustering of galaxies. Okay. Questions before I move on to another thing? No? Okay. There's one other effect that plays a role in the clustering of photometric galaxies, which is something called magnification bias. I'm not sure if you've heard about this. Well, it plays a role in any clustering, but in 2D clustering it's particularly important. Right. All right, so what did we say we measure? We measure the number density, the projected number density of galaxies, right? The angular number density of galaxies. That means dn, d omega, where this is the observed angular, the observed solid angle. Let's imagine that we're doing this for galaxies that we've selected by just looking at the sky and selecting all the galaxies that are bright enough. So we put a cut on their fluxes, right? So we only do this for galaxies with a flux larger than a given flux limit. So those that are bright enough. Okay. Okay, we've seen that weak lensing will distort the solid angle between a set of galaxies, right? So this solid angle that we observe for a given range of galaxies, this is not actually the same solid angle that these galaxies would occupy if there was no lensing. So we can write this as d omega true, so the true solid angle, divided by d omega observed. Then I'm gonna use the chain rule once more and say that I'm gonna introduce the volume occupied by these galaxies as a function of the solid angle that you're observing. And then the rest would be the number of galaxies per unit volume within the flux limit. Okay. We saw this before when we looked at weak lensing. This is just 1 divided by 1 plus 2 kappa. And we said that through the displacement field, so through the lensing displacement, basically, we are washing out structure. So we will suppress the number of galaxies by or the number density of galaxies by 1 over 1 plus 2 kappa. And then we have dv d omega true. And then what is this? This is the number density per unit volume, sorry, the number of galaxies per unit volume, which we can write in terms of the cumulative luminosity function. So the luminosity function is like the mass function, but for luminosities, how many galaxies we find with a sufficiently large luminosity. Remember that the luminosity then needs to be larger than the corresponding luminosity for this flux limit. So this would be 4 pi, the angular diameter distance squared times the flux limit. But remember that fluxes are also affected by weak lensing, and they're affected in the same way, right? So the flux that we have observed is not the true flux, and to account for that, there's another ratio with 1 plus 2 kappa, right? Yeah. Plus 2 kappa. Remember that we had this effect, right, where if we have background sources, and then we put a lens in the middle, those sources, their observed angles will move away from the lens, right? So they'll appear to be farther away from each other. And so that will decrease the number density of these objects, right? And we saw that it decreases that by a factor of 1 plus 2 kappa. So that's where it's coming from, right? Is this ratio of angles. We saw that the same effect, the kind of expansion of the solid angle, will also affect the measured fluxes of galaxies. Okay. All right, so if we take this, we know that the lensing effects are usually small, so we can do a Taylor expansion of all of these. I'm not going to go through all the steps, so you can do it yourself. But the final result is that the observed number density will be equal to the true number density, dn d omega true, times 1 plus 5 times s. I'll say what s is in a second, minus 2 times kappa. And S here is a parameter that we often call the magnification bias parameter. Some people will call the Hall effect magnification bias. But anyway, S is the logarithmic derivative of the number counts as a function of magnitude. And here's a word that makes everyone cringe, magnitude. With respect to, so it's the logarithmic derivative with respect to magnitude at the magnitude limit of our sample. Is everyone familiar with how magnitudes are related to fluxes? Blank stares and some nodding. Okay. So it's one of them is kind of the logarithm of the other one with some prefactor. Look it up. I express it in terms of this because usually in a galaxy sample, you will get the magnitudes of those galaxies, right? So this is something that you can calculate directly for any galaxy sample. All right. So that means that lensing gives us an extra contribution to the clustering of galaxies, right? So an extra kind of distortion in the number counts of galaxies. But where's that coming from, like physically, let's say? So we said we have two effects. We have the expansion of the angles that kind of suppresses the clustering, right? And that's where this -2 comes from. So you get a negative overdensity due to lensing, and that comes from just lensing kind of displacing galaxies away from each other. But we said we also have flux magnification, right? So let's imagine what we're doing, right? Let's say this is, as a function of magnitude, the cumulative number counts of galaxies that we have in our sample. Remember, annoyingly, large magnitudes means fainter galaxies, okay? So let's say it usually looks like that. It usually looks like a power law. This is log-log plot. All right. flux magnification means that galaxies that are fainter will appear to be a bit brighter due to lensing, okay? So let's say that we're only including galaxies up to this magnitude limit. Flux magnification will take some of the galaxies that were at a higher magnitude, so fainter galaxies, and they will bring them into our sample, right? It will also, if we had a negative value for kappa, it would also make some galaxies fainter and bring them outside. But because this is a decreasing function, this usually wins, right? And so that gives you this positive contribution to the clustering of galaxies. So this part here comes from flux magnification, and this comes from the washing out of structure due to lensing. Okay, and it all depends on the slope, right? So if you had a flat distribution of galaxies, right? So if this was flat, these two will compensate each other, right? So that's why that would be if S was equal to 0 in that case, right? So that's why it depends on the slope of this curve. Okay. Right. So why is this important? Well, it's important because we need to take it into account. So when we observe the 2D density of galaxies, that will be the kind of intrinsic or true overdensity of galaxies. So that's the one that we said is local in redshift, right? But you'll also get a contribution in the form of 5s minus 2 times kappa. This is both good and bad. I think it's mostly good, actually, because that means that, because S is something that we can always calculate from our sample, right? We just do kind of a histogram of our galaxies and just calculate the slope. So this is not unknown, right? We can always calculate this. And this is a contribution that is purely lensing, and lensing doesn't have any bias, right? So if we can isolate this contribution, we can actually constrain sigma 8 from galaxies, right? So that's kind of nice. However, this contribution, which I'm going to call delta mag, or delta m, this contribution is usually much, much smaller than this one, okay? So that usually means that if you're looking at the autocorrelation of galaxies with themselves, this dominates, and this is usually unobservable. This is very small. But what can we do to extract it? There's two different games we can play. One of them is, let's say, okay, we have galaxies here, and these are the ones that we want to use. And let's say that we also have galaxies somewhere else at lower redshifts, right? If we look at the cross-correlation between these two, if there was no magnification bias, there should be 0 cross-correlation, right? Because these are local. This is Z. This is the P of Zs of the galaxies, right? So in this cross-correlation, if there's no magnification, there should be 0 signal. But with magnification, you should pick up some signal, because remember, the kernel associated with kappa is a broad kernel that looks like that. And so it overlaps with the lower redshift galaxies, right? So the cross-correlation between this and this will pick up a cross-correlation between the intrinsic clustering of these galaxies and the kappa part, right? So I think I have an example here of that. This is from a recent paper this year, actually. Yeah, this is Seiler et al. 2025. So these are galaxies in the DESI legacy survey, and divided up into different redshift bins, right? So you have 6 of them. And what you're seeing here is the cross-correlation between one of these 2 redshift bins at low redshifts and one of these 2 high redshift bins, and you can see that the redshift distributions don't overlap at all, right? And you can clearly see a signal that is non-zero, right? It's highly significantly non-zero. So this is one of the strongest measurements that I've seen of magnification in galaxies. So this is a clear example of how you can use this to extract sigma 8 from these galaxies. Does that make sense? We would expect, we know this factor, right? So we always know what this is. So we know how large the contribution from magnification bias in principle is. Let's say I'm going to call this sample L for low redshift, okay? So let's say that we're looking at the cross correlation between L and and the high redshift bin is going to be h, okay, LH. Right, so this will be proportional to what? Proportional to sigma 8 squared, because everything is proportional to sigma 8 squared. It's going to be proportional to the bias of the low redshift galaxies. And then it's just going to be proportional to 5s minus 2, right? Because it doesn't receive any contribution from the actual clustering of the high redshift galaxies, right? And this we know. This we know. This we don't know. And this is what we want to calculate. But this we don't know, but we can just get it from CLLL, right? CLLL will be sigma 8 squared, BL squared, let's say, right? So we combine these two, and then we can figure out what sigma 8 is. Yeah. Well, I mean, this is galaxy clustering, right? We will still, in the sense that what we will do is we will have two maps of the overdensity of galaxies at high and low redshifts, and we will cross-correlate those two. We haven't looked at the shapes of these galaxies or anything like that. You don't have a measurement of the lensing effect, let's say, itself. It's just that the clustering, the observed clustering of these galaxies is affected by the line of sight distortions of the photon trajectories, basically. Yeah. Yeah, that's right. Yeah. Yeah. That's those power spectra. If you go to the same paper, then you'll see the LL versions of that, and then comparing those two, you could eyeball sigma 8 if you want. Yeah. Will depend. Yeah. So from here, you'll be able to constrain BL sigma 8, right? So that means you'll know what this is, right? So then you can measure sigma 8. Yeah. Yep. Yeah, usually it's very negligible. Yeah, at very high redshifts, maybe you should worry about it, but in autocorrelation, it's always really, really small. Yeah. Yeah, exactly. Yes. Yeah. So if you look at CLHH, right, would have three terms, right? It would have the CL of the intrinsic clustering with itself, I for intrinsic, meaning the local term, right? The cross correlation CLIH and the CLHH. Sorry, kappa or magnification, let's say MM. And this is super large compared to these two. Yes. So if they were overlapping, right? If this one had a long tail like this, then this measurement is going to be a mess, right? Because it's going to be very sensitive to this overlap here. Is exactly. Well, so if you have perfect control over this redshift distribution, so you know it really, really well, maybe you can still tease out this term, right? The magnification term from it. But usually what that means is that the amplitude of that cross correlation will depend on magnification, but also it will depend on this tail. And usually you don't know the tails of the redshift distribution super well. So yeah, so it gets tricky. What's nice about DESI is that those redshift distributions are known quite well, because the DESI legacy survey has a lot of spectra as well. So those redshift distributions are known quite well. And so you can trust that they don't overlap very much in that case. Yeah. Yeah. Does that make sense? S was the slope of the number counts of galaxies that you have as a function of magnitude, right? Say again? Yeah, so that, let's say, right, so that plot was as a function of magnitude, meaning the brightness of our galaxies, and these are fainter galaxies and these are brighter galaxies. What is the cumulative number of them, right? So meaning if we go to fainter and fainter objects, how many can we see, right? And so it will be a monotonically increasing function, because the fainter you go, the more galaxies you collect, right? And let's say you stop at this point, right? So your sample of galaxies is all the ones that are brighter than a given magnitude. S is basically the slope this curve at this point is the tangent of it at this point. And it basically tells you, if you have lensing, how many galaxies you're going to bring in from this side into your sample, basically. Yeah. Okay.
Why do the bins overlap in the first place? Like, can you choose like a more like top hat light
So this data is not from the DESI survey. DESI is a spectroscopic survey in which you could do this. This comes from the DESI legacy survey, which is the photometric survey that preceded DESI, right? So these are galaxies that are selected by their photometric redshifts. So that's why you can't make them exactly top hat, because you can't say, okay, I want my... Yes, exactly. So those tails come from the redshift uncertainty of the photoseas. What I was saying is that the shape of that redshift distribution, we know it very well because DESI also has a lot of spectroscopic galaxies, and they can use those to reconstruct the redshift distribution. Yeah. Yeah. Yeah, so if you could do this with spectroscopic redshifts. The problem with spectroscopic redshifts, and this is, okay, let's talk about this because then I'm going to be able to use this tomorrow, actually. Right. We haven't talked about the noise of galaxy clustering, right? When we talked about weak lensing, we said if we get a measurement of the ellipticity is going to have two components. It's going to have the shear component, which is the signal that we're interested in, and then there's the noise-like individual shape of the galaxies, right? We said E is equal to gamma plus En, where this was the uncorrelated part that we don't care too much about, right? In galaxy clustering, it's a bit different, but it's a very similar effect. The way to think about galaxy clustering is what we're measuring are discrete objects, right? And we're counting them. You could think of that as basically saying the density of galaxies that I observe, let's say even the number of galaxies that I observe in a given point, in a given region of space, is a Poisson sampling of the mean number of galaxies that I should observe here, right? And I'm only observing a single realization of that Poisson process, okay? So that means that what you observe, the measured overdensity of galaxies, is going to be the true underlying kind of smooth overdensity of galaxies that would tell you what the mean number of galaxies should be in a given region of space, plus some extra noise. And that noise term comes from the Poisson noise of that particular realization that you've chosen, okay? So when you look at the CL of galaxies, what you'll get is the angular power spectrum of the underlying smooth distribution of galaxies, CL, GG, signal, let's say. So the part that you care about. But the Poisson noise will give you an extra contribution. Poisson processes are uncorrelated across different points in space, so it's also going to be a white-like noise component, right? And it goes like 1 over the number density of galaxies, in this case, the angular number density of galaxies. Okay, so the CL measured, the CLGG, would look like this, except there's Poisson noise, right? So in reality, what you measure ends up being something like this, right? And you can always subtract Poisson noise because you know exactly what it is. You just measure the number density and subtract it. But it will act as a source of uncertainty here, right? So it will contribute the same way that this contributed to the error bars of the lensing power spectrum. This will also contribute to the error bars of the lensing power spectrum. Okay. This connects with your questions. Why? With your question, why? In a photometric survey, we said what you do is you just take a picture of the sky and just count galaxies above a given magnitude limit, right? And you're done. But you can do it for all the galaxies that you've taken a picture of. In a spectroscopic survey, you can't, right? Because you first do that, and then you say, okay, now I need to spend quite a long time measuring the spectrum of this galaxy, and then this other one, and then this other one. So that's a lengthy process, right? You can't do this for all the galaxies that you observe. So that means that for a photometric survey, this thing is usually quite low. So the shot noise is usually quite low. For something like LSST, you can almost ignore shot noise because it's so small. For a spectroscopic survey, this is usually much higher, right? So there's a trade-off. You can, in a spectroscopic survey, the good thing for these kinds of things is that you'll be able to slice things up into very well-defined redshift bins. The problem is that you'll have a lot of shot noise. So maybe this kind of measurement will be swamped by that shot noise. Those error bars there could be a lot more dominated by shot noise, in which case you don't see the signal anymore, right? That's the problem. Yeah. And we'll come back to shot noise tomorrow because I want to show you how to measure a power spectrum in practice, and we'll need to deal with shot noise. So remember that for tomorrow. More questions? No? Okay. The last thing that was not systematic that I wanted to talk about is what we mentioned two days ago, the idea of 3 times 2 point, right? But I think we actually have covered everything we need to cover for 3 times 2 point, because 3 times 2 point is nothing more than including all the auto and cross correlations we can get from galaxy clustering and cosmic shear, right? In a photometric survey, photometric surveys are particularly useful for weak lensing, right? Because the main thing we care about for weak lensing is having good images of our galaxies so we can measure the shapes of those galaxies. But since we're measuring the shapes of those galaxies, we can also count them, right? So with a cosmic shear survey, you always get both observables. You will get gamma and you will get delta G. You will always be able to do both. Don't move too far away because I'm going to start. So yeah. So 3 times 2 point is essentially the joint analysis of the autocorrelation of galaxies. This is often just called cosmic shear, but so the autocorrelation of the shear, right? And sometimes people just call it cosmic shear. I like to think of it as an autocorrelation. The cross correlation between cosmic shear and galaxies, and then the autocorrelation of the galaxies themselves, right? Delta G, delta G. And it's the joint analysis of all those two. That's what 3 times 2 point means, is the 3 different 2 point functions that you can construct if you have 2 observables, okay? I think we've thought about all of these, actually, right? So how do we use 3 times 2 point in practice based on what we know? So maybe the thing that we haven't talked about too much, we have actually in the context of CMB lensing cross correlations with galaxies, so it's the same idea with cosmic shear. The thing we haven't talked about too much is the cross correlation between shear and galaxies, but again, it's the same idea as cross correlations between CMB lensing and galaxies. So this is an example of those cross correlations. This is from DES, from the first data release from DES. So this is actually a very old measurement. These are cross correlations between galaxies in different redshift bins in this direction, and cosmic shear in different redshift bins. So that's why you have so many different measurements. Can anyone guess why those measurements here have very clear signal-to-noise detections, but those here don't? So this was basically the cross correlation between galaxies, let's say in these redshift bins, 4 of them, 1, 2, 4, 5 of them. Okay, 1, 2, 3, 4, 5. So this is the galaxies, and then the cosmic shear part was also samples of galaxies at different redshifts, and I think they looked something like this, basically. Maybe I'll do those in a different color. So based on this picture, can anyone guess why the signal-to-noise of those cross correlations is so low, the ones at the bottom left? Yeah, exactly. So for any of the shear samples, right, the lensing kernel will do something like that, right? And something like G4S0, that means shear in the 0th redshift bin, galaxies in the highest redshift bin, there's no overlap between these two, right? So that's why you expect those to be 0, actually. Anyway, so how do we extract information about from 3 times 2 point? And I think we know everything we need to know in order to guess that. My picture of it, which others might contest, because it's actually, there's a mixture of information in all of these cross correlations, but I think the shear autocorrelation, the main thing it tells you about is the overall clumpiness of the universe, so how large the density fluctuations are. And the reason why I say that, that's that. And then the combination of shear cross galaxy and galaxy times galaxy, so this is what often people call 2 times 2 point, tells you about the shape of the power spectrum and the growth of structure, so the evolution in sigma 8 rather than the overall value of sigma 8. And we already saw some of these, right? So remember that, first of all, weak lensing, which is the only thing that is involved in shear, there's no bias, so we can measure sigma 8 for sure. But it's line of sight integrated. It's cumulative. It's not local in redshift. And we said that there were several things that come with that. One of them is it's going to be less sensitive to evolution, so you're not going to be able to say much about the evolution of perturbations with time. We said it's more sensitive to small scales because of the low redshift tail of the lensing kernel. And also because you're mixing so many different redshifts together, you're going to lose information about physical scales, right? Because they will all contribute to a broad range of angular multiples. So you don't get much information from the scale dependence of the power spectrum. You get some because you have a little bit of a tilt, right? But overall, the shear power spectrum is boring. It's boring because it just looks like a power law, but it's a power law whose amplitude you measure really, really well. So that's why I like to think of cosmic shear as a really good measurement of the overall amplitude of the power spectrum. So it's really good at measuring that. And then we said for galaxy clustering, we have the same picture as the other day, right? Where we were seeing any correlation that involves galaxies is going to receive contributions from a very specific set of redshifts, because galaxies are local. So that's both for shear galaxy and for galaxy-galaxy. Which means that 2 things. First of all, it's going to be sensitive to scale dependence, because you can relate a given angular multiple with a given physical one, so you will be able to resolve those. Remember, these for cosmic shear look like super broad kernels that mixed up all the different scales together. So it's going to be sensitive to the scale dependent, meaning that you'll be able, for example, to recover the tilt of the power spectrum a bit better. You'll be able to recover potentially BAOs, but we said maybe not in the best way possible. But also it's sensitive to evolution, right? So you can use this tomography trick to measure sigma 8 as a function of redshift by slicing up the shear with galaxies at different redshifts, right? So it may not be the best measurement of the amplitude of sigma 8, but it's the best measurement of the evolution of that amplitude with redshift, okay? So it tells you something about growth. And so ultimately, if you look at the usual 3 times 2 point analysis, this is the kind of constraints that you end up getting. You get very good constraints on 2 parameters, sigma 8 and omega m. Omega m is through both the growth, the scale dependence of the power spectrum from the 2 times 2 point, and from the relation to the distance redshift relationship, basically. So it's kind of like an Alcock-Paczynski effect, but for angular power spectra. So you get that, and you get sigma 8 definitely from lensing as well, right? And very often, because the constraints tend to look like this, we combine those constraints into a single parameter. There is this weird combination of sigma 8 and omega m. That's the parameter that goes in this direction. So it's the one that has the smallest error bars, basically. We usually call that S8. And you may have heard about the S8 tension. You can ask me about that later if you want. But yeah, this is the parameter that is best measured nowadays by weak lensing, 3 times 2 point analysis, basically. Yeah. Not really. I think so. You can guess that there should be a combination of sigma 8 and omega m because you have very strong. If you don't have very good redshifts, you don't know the distance. You don't really know the distance to your galaxies very well. So recovering information from the shape is going to be degenerate with omega m to some extent. So you could guess that it's some combination of these two. But whether this is 0.5 or 0.3 or 0.4, it usually depends actually on the specific setup that you have of galaxies, et cetera, et cetera. So it's very common to just talk about this one because this is close enough to the optimal for most galaxy surveys. But some galaxy surveys measure a slightly different parameter better. So forget if HSC I think the best one they get is for this being 0.3, I think, or something like that. So it's not an a priori thing that you could predict necessarily. Yeah. Yeah. Yep. So I wanted to have spent some time talking about the main systematic effects that affect these kinds of measurements. And clearly, there's no time for that. So maybe I'll just flash a few things through in the last 5 minutes, just to give you an idea of what are the main things we need to worry about when we look at galaxy clustering and cosmic shear in terms of effects that could bias our measurements. But I won't go into the details too much. We can talk about that in the Q&A or later on. Right, so when we're trying to interpret information from 3 times 2 point, meaning shear and galaxy clustering, what are the main things that we need to worry about? Well, for galaxy clustering, remember the main thing we care about is measuring the actual number of galaxies or the number density of galaxies in a given region of space, right? So literally, and we will see this tomorrow, what we do is we take our catalog and count how many galaxies there are in a given pixel, okay? And if everything was ideal, that's it, right? Those galaxies would be all the galaxies that are in that pixel. But in reality, that's not the case. We have systematics that might modulate the actual number of galaxies we observe, right? And the easiest one to understand, for example, is extinction from our galaxy. Sorry. This is going to be like that for a while. So what is extinction from our galaxy? The idea is our galaxy, we have to look through the Milky Way in order to look at the universe. And the Milky Way has a lot of stuff. And part of that stuff is dust. And dust, for those, I'm not sure how many of you are astrophysicists, but dust is really, micrometer-sized large molecules, effectively, or dust particles, right? And at those sizes, they absorb a lot of the optical and ultraviolet light. And so we can't really see through a dust cloud the same way that we can't see through dust on Earth, because light gets absorbed and scattered by dust. So this is an example, actually, from a region of a galaxy, of our galaxy, where we know there's a big cloud of gas, and you can see that there's this big void, and this is not because there's anything weird with the universe, it's just that you have a lot of dust along the line of sight. And so that dust, for example, and that's just one example of a potential systematic, will modulate the actual number of galaxies that you measure. So that can give you a bias in the measured power spectrum. So the idea is we try to map out as many of these potential systematics as we have, and we try to subtract or fit out their contribution in our measurements. But that can be tricky to do. So that's the first systematic. I usually call this just sky contamination. The other one, so this is for galaxy clustering. For cosmic shear, the main problem we have is shape measurement. We said that the main, what we want to do is to have an image of a galaxy and measure its ellipticity. And that's to give you an idea of how messy that can be when you do it for very faint galaxies, which is what we need to do for LSST, for example, or DES. So let's say this is the perfect image of a galaxy on the left-hand side. And then cosmic shear, weak lensing will shear it a little bit, right? And that's kind of the effect we're trying to measure. So it's not a very strong effect. Then the photons coming from that galaxy, they will be scattered by the atmosphere, and they will be further, our telescope doesn't have infinite resolution, so they'll be blurred by our telescope. So you end up with that kind of picture. And then not only that, but for optical telescopes, this is not what you do, right? Those photons then need to hit a detector, and that's what you see. You see the kind of the voltage peaks in the detector. And those detectors have a finite resolution as well, so you end up with a pixelized image like that. And then those are not all the photons that you've detected. You've detected those photons plus all the other photons coming from anywhere else in the atmosphere, on Earth, on whatever, right? And even just noise in the detector itself that is not even a photon, it's just noise. So your image in the end looks like that. And so if you try to extract the true ellipticity of that galaxy from that, that's not going to be easy, right? So shape measurement, the systematic associated with shape measurement is basically the fact that if you take that image and try to infer its ellipticity, you won't get it always right. You'll get a biased measurement of that. And the way we deal with that usually is to apply our estimators for ellipticity to simulations, right? So we literally do this, right? So you take the image of a realistic galaxy, you pass it through a pipeline that imposes all the different instrumental effects that go into the final image, including noise. And then you measure the ellipticity, and you do this for many, many, many simulations. And from that, you figure out what are the main effects that bias your inference of the ellipticity, and then correct for those afterwards. Okay. I can go, don't have time to go into more details, but we can talk about how that's done later. And the final one, and I'm already 1 minute over the time, is photometric redshifts. And this is a big one. So photometric redshifts are basically the redshifts that we assign to a galaxy based on their photometry. And they are very, very different from their spectroscopic redshift, right? In an ideal situation, each galaxy would come to us with a conditional probability distribution that tells us what is the probability that this galaxy is at a true redshift ZS, given what I've measured, which is the photometric redshift. But it's ludicrous to assume we can get a very good estimate of this for realistic galaxies, because we actually don't know this very well, right? So this is not often what we get. So different photometric redshift codes will give you an estimate of this, but usually you can't rely on it. Fortunately, for this kind of angular analysis, the main thing you care about is not really the PDF of a single galaxy, but the cumulative redshift distribution, right? What we've been calling the P of Z. So for my sample of galaxies, what is the global distribution of redshifts in that sample? And so there's different ways of trying to estimate this. One of them is to try to have a few parts of your survey that overlap with a spectroscopic survey and try to measure the true spectra for some of these galaxies. The main problem with that is that you are probably not going to be able to measure spectra for a representative sample of your galaxies, meaning the same fraction of galaxies as a function of color, the photometry of these galaxies. So you will probably only be able to measure spectra for galaxies that are sufficiently bright, for example, or galaxies that have been targeted by a particular spectroscopic survey. So there's going to be a mismatch between these galaxies for which you have spectra and the ones that you don't have spectra for. And you need to correct for that, and there's different ways of doing that. So that's one option. The other option is to, the other option I'm not going to talk about because I'm running out of time, but it's something called clustering redshifts. And if you want to know more about, maybe ask me about that, or during the Q&A or later. But there's another technique called that. Right, okay, that's all I wanted to say, and I'm already over time, so let's stop here. Yeah, thank you.
Thank you, David. So questions for David?
Already overwhelmed everyone, I think. Yeah.
Yes, just a second.
Because in some literature, I think you mentioned that cross-correlation function is more Gaussian than the auto-correlation function. Can you explain why this?
Say the beginning of the question again?
Yeah, why the cross-correlation is more Gaussian than the auto-correlation function?
And when you say Gaussian, you mean that the statistical uncertainties of our measurements are better described by a Gaussian distribution than an autocorrelation. Well, I think it depends on the scales that you're looking at, but one way of seeing why that would be the case is imagine that, so let's say that you have a field A, and you're measuring the power spectrum. How do you measure the power spectrum? We'll see that tomorrow, but a teaser, right? And this is something that Manu has also written, is you essentially do an average over all the M modes, something like that, right? 2L plus 1 times ALM squared. And you can see that by construction, this is a positive definite quantity, right? So if you want to look at the probability of measuring a given CL as a function of the value of that CL. This CL can never be negative, right? So if the measured CL is this and your error bar is this, your probability distribution is not going to be a Gaussian that looks like this, right? The probability distribution has to die off like this for sure, right? Because you cannot have a negative CL by construction, right? So this is an easy way of seeing why that is the case. For a cross-correlation can be negative, no problem, right? So cross-correlation CL between fields A and B, you would do the same thing, 1 over 2L plus 1, sum over M, and then the real part of ALM, BLM. This is an E. Right, and there's no reason why this cannot be negative. So in general, yeah, that can be perfectly negative. So that's I guess, an easy way of seeing why that is. The other way of seeing why that is imagine that you're in the situation where one of these is a very well-measured quantity, the other one not so much, right? So you could even think of this as being a fixed quantity and this fluctuating. So that means if this is Gaussian and this is fixed, you basically have a Gaussian error on the final CL. That's one way of seeing that. But that cannot apply to autocorrelations because they both, it's the same field twice, right?
Yes, thanks.
Yeah.
More questions? Okay, so let's thank David again for this nice talk.
Thank you.